The International Diabetes Federation predicted the prevalence at 536.6 million as of the year 2021. The prevalence has been predicted to rise up to 783 million by the year 2045. There are quite a number of causes and risk factors. To mention a few: urbanization, reduced physical activity, and high prevalence of obesity. There are so many other risk factors such as age, overweight, physical inactivity, unhealthy diets, tobacco use, and family history. So quite a number of drugs are used in management of diabetes mellitus. Very important drugs: the oral hypoglycemics, the biguanides, metformins, sulfonylureas, gilbines and glipizides, and the glitazones. But however, these drugs are quite expensive, but also associated with a number of adverse effects, and also non-curative. Locally in our community, a number of plants are used in management of diabetes mellitus. But one of the important plants used by our community is this, aloe vera. In Uganda, it's called echigaji. I think in Ateso, it's called edoido. Very useful plant, traditional in management of diabetes mellitus. And the pharmacological properties of this plant have been associated to one of its important compounds, that is aloemodine. So scientific studies have evaluated the different pharmacological properties of this compound, and it has been reported that aloemodine has potential anti-cancer properties, it has potential anti-inflammatory properties, it has potential hepatoprotective properties, and microbial properties. But importantly, how does it work? It is a big question, and it's a question that applies to most of our herbal medicines. How do they work? That is unclear even to aloemodine. So at NAPRIF, we decided to use computer-aided approaches to understand, to elucidate the possible mechanism of action of aloemodine. And aloe vera is also a key ingredient in one of the products that we're developing at the center. So it's very important we understand how our product treats diabetes mellitus. So allow me to take you through our journey. How did we conclude with aloemodine? Of course, we started with the literature. So there's overwhelming literature about the various pharmacological properties and activities of aloemodine through databases like PubMed, Google Scholar, Inari, PubChem, Cielo. Aloemodine is overwhelmingly reported and mentioned in all those databases. So the next thing we did is to understand the drug likeliness, the pharmacokinetics, and the toxicities of our compound aloemodine. So we used online platforms to understand the pharmacokinetics, how aloemodine is absorbed, how it is metabolized, how it is distributed and perhaps eliminated in the body, and also the potential toxic effects of aloemodine. So the next thing we did is to understand what are the possible targets of aloemodine in the body. What molecular targets does aloemodine interact with in the body? So we used a number of bioinformatic platforms like SuperPredict, TargetNet, Swiss Target Predict to predict the possible targets of aloemodine. The next step was to understand, to collect and mine the various potential targets for diabetes mellitus, drug targets for diabetes mellitus. And we got these targets from a number of bioinformatic platforms like GeneCards, DisGenet, and Omic. So after collecting the potential targets for allohemodine and the various targets for diabetes mellitus, we established associations between these two. Are there any links, are there any connections between the potential targets of allohemodine vis-a-vis the drug targets for diabetes mellitus? And in this, we're able to come up with a network. We constructed a network made up of various proteins. So, which proteins are encoded by genes? So we did the gene ontology studies to understand the various cellular processes that these genes are involved in. So the next thing we did is to do cake analysis to understand the various pathways that these genes are involved in. And another thing that we did is to now dock. We assessed whether allohemodine can dock or can bind to these potential targets, and we did molecular docking. Of course, we prepared our targets, and those are the genes or the proteins, and also prepared our ligand, that is allohemodine, and then we use autodock tools and other very important softwares like Avogadro, Chimera X, Discovery Studio to understand how allohemodine interacts with the potential targets in diabetes mellitus. And through this journey, we've been able to elucidate the possible mechanism of action of allohemodine, which is a key phytocompound or phytoconstituent in aloe vera. So these are our results. To start with, the drug likeness or the drug likeness prediction, the pharmacokinetics and toxicities of allohemodine. Does allohemodine look like a drug or a potential drug? This is what these results are informing us. So important parameters were assessed. Number one, we see the molecular weight. And allohemodine has a molecular weight of 270.24 daltons. When given orally, allohemodine has a very good oral absorption. So that means it has a very good or unappreciable bioavailability. When you look at how it is metabolized, two important enzymes metabolize or inactivate allohemodine. One of them is CYP1A2 and also CYP3A4. This informs us that there is potential drug interactions because these key enzymes are also involved in the metabolism of quite a number of drugs that we use clinically. But we also assess the bioavailability score, how much of allohemodine can get into the systemic circulation. And our result is it has a bioavailability score of 0.55. So the next thing we did is the potential organotoxic effects of allohemodine. And from our findings, allohemodine has no effects on the liver, it has no effects on the skin, it's not a carcinogen, but importantly, there is potential for skin sensitization. So, in summary, this ladder represents the pharmacokinetic properties of allohemodine. It has a very good lipophilicity, it has a very good size, it has a very good polarity, it is not insoluble, it has a very good saturability, it has a very good flexibility. Then we applied a very important rule, what we refer to as the Pisiki rule of 5, for any orally administered drug should at least conform to these 5 rules. Rule number 1, any compound, any drug should not have more than 500 bond donors. And then allohemodine had 3 hydrogen bond donors. Next, not more than 10 hydrogen bond acceptors. Allohemodine had 5 hydrogen bond acceptors. Molecular weight, not less than 500 daltons. Allohemodine has a molecular weight of 270.24 daltons. And lastly, a lipophilicity of not greater than 5, or a clog P of not greater than 5. Allohemodine had a very good result in this regard, a clog P of 1.82. So this informs us that actually allohemodine is a potential drug candidate. So also rotatable bonds, it has 1 rotatable bond. And the next thing we did is to identify the potential targets of allohemodine. So these are our results. Allohemodine has 237 potential targets in the body. There are 703 possible targets for diabetes mellitus, drug targets for diabetes mellitus. So we analyzed the intersection between these two, and we identified 32 genes that are common with allohemodine and with diabetes mellitus. So we constructed this network, but however, this network may not make sense unless you do some statistics. So we identified that actually these proteins or these targets are highly enriched, or they are associated, they are interlinked. This gave us confidence to move up to the next stage, or to the next step. So the next thing we wanted to understand is the different cellular processes that these genes are involved in. Number one,
you can summarize in 3 things.
Okay, thank you. Number one, in terms of biological processes, our genes or our targets are involved in the negative regulation of apoptotic processes. But also, they are involved in the positive regulation of transcription from RNA polymerase. In regard to cellular components, they interact with components in the nucleus, components in the cytosol, and components in the cytoplasm. In regard to molecular function, these genes are involved in identical protein binding and enzyme binding. So the next thing we did, the cake enrichment analysis, understanding the different pathways that these genes or the protein that they code for are involved in. We noticed that they are involved in a number of pathways, and the topmost is apoptosis, the second is lipid and atherosclerosis, but importantly, at the bottom, we noticed that these targets or proteins are involved in insulin resistance and in the pathophysiology of pathogenesis of type 2 diabetes mellitus. This gave us confidence to move on to the next stage. So the next stage was to identify what are the hub targets, what are the key genes that are associated with allohemodine and highly associated with allohemodine vis-a-vis diabetes mellitus. So we identified the hub targets, and we applied 3 important algorithms. One is the maximal click centrality, the maximum neighborhood component, and the degree of nodes. So we identify these 9 genes as the key genes that if we are to develop allohemodine into a drug, these are our possible targets. We noticed that we have proteins like the tumor protein 53, epidermal growth factor receptor, saturnin 1, albumin, the beta cell lymphoma 2, caspase 8, tumor necrosis factor. And when you read about these genes, they are highly associated with the pathogenesis or the pathophysiology of diabetes mellitus. So the next thing we had to do is to do docking. Okay? These are the hub targets, but how will they associate or interact with our ligand, which is allohemodine? we noticed that they all have very good binding affinities. But importantly, we noticed two important targets. That is tumor necrosis factor that has the highest binding energy of -7.75. And these are its residues, but also identified another target, important target, the peroxisome proliferated activated receptor gamma. And that is a very important target. Why? Because quite a number of drugs and diabetic drugs on market, the glitazones, drugs like dosiglitazone, pioglitazone, which are very good drugs management of diabetes mellitus, are actually agonists of this receptor. And the interaction demonstrated a very good binding affinity of -7.27. So this gave us more evidence to move on to the next step of understanding now how these are the docking images. I want to conclude with the results of molecular dynamic simulations. The story would be incomplete if we don't do molecular dynamic simulations. So we wanted to understand how the ligands interact with the target or the proteins, for how long, and how close the proximity of this interaction. That is why we did the molecular dynamic simulations, and our results show that there is a good interaction between tumor necrosis factor and PPAR gamma with our ligand, that is allohemoglobin. So from the interest of time, let me move to this. Our major purpose was to decipher the possible or the potential mechanism of action of allohemoglobin. And this is what we concluded with. With allohemoglobin targets a very important protein, that is tumor necrosis factor alpha, that is involved in the modulation of a number of downstream messengers, second messengers, that are involved in the pathophysiology of diabetes mellitus. So that is one possible mechanism of action of allohemoglobin. And tumor necrosis factor is involved in pathophysiological processes like the pancreatic beta cell apoptosis. So if we are able to target and block its effects onto these downstream second messengers, we could be able to control diabetes mellitus. But also, lastly, we can target the receptor PPAR gamma. That receptor is involved in a number of processes. Importantly, in adipocyte differentiations, in fatty acid storage, and glucose metabolism. That is why the drugs that I talked about are very important in management of diabetes mellitus. So our MOD is similar, will also manage diabetes mellitus by targeting this important pathway. So we conclude by saying that allohemoglobin exhibits strong binding affinities for tumor necrosis factor alpha and PPAR gamma. However, it's important to note that this is a purely in silico study, in computer. So to validate these findings, we need more advanced in silico techniques, but also more in-depth in vitro assays and more in-depth in vivo experiments. So the in vitro assays are currently undergoing at Uganda Virus Research Institute, but also the in vivo experiments are being undertaken at COVA, Makerere. We acknowledge our partner, that is STI, OP. Thank you for listening.
Thank you very much. Wow. Very inspiring.
The required or plasma concentration of this compound to offer a therapeutic or to cause therapeutic effect.
Napoli has done a lot of work, especially with herbal formulations and very good. We need to work hard for ensuring that African medicine is coming up professionally. However, I have not seen deep. Let me use deep because there are people using like deep learning, deep everything, deep tech, deep. So I haven't seen deep collaboration between Africa and the Faculty of Engineering. Why? For instance, some of these drugs, I would think of, now if we have a microscope is like 5. How about maybe exploring using patches, lunar technology, something you can put on the skin and the drug, is absorbed in the bloodstream. And this is where engineering will meet and approve and develop some of these categories. So I haven't seen that yet.
Yeah, sure. That is a very important point for pushing forward. And one of our chief scientists, that is Dr. Nima Moses, is leading us towards that. He's a very good guy when it comes to, very good scientist when it comes to nanotechnology. And hopefully you'll be able to establish a collaboration between Africa and